What's up everyone? Welcome to today's video where we will cover the edit distance problem and how it can be solved using dynamic programming. Let's get started. The edit distance problem is a problem where you are given two strings and are asked to measure how different they are using some metric. For today's example, we will be determining the minimum cost of aligning two sequences of DNA. Given two DNA sequences, you have the choice of adding a gap to one of the sequences, aligning a mismatch, or aligning a match. A gap has a cost of 2, aligning a mismatch has a cost of 1, and aligning a match has a cost of 0. Given these values, we want to find a minimum cost of aligning two sequences of DNA. First, let's take a look at a standard recursive way of approaching this algorithm. With any given set of DNA, our focus lies on the first character of each sequence, and in that moment, we want to determine how we will deal with the characters. We have three choices to pick from: adding a gap to the first sequence, adding a gap to the second sequence, or attempting an alignment. We want to try all three options since we need to know which one will result in the minimum overall total cost. For every operation we perform, our inputs will move on to a smaller subset of the original problem, and we will want to find a minimum cost of that subset. This is where we get that recursion. The animation you've been watching demonstrates the sequence of operations that results in the minimum cost. For example, given the two sequences ACTG and CTA, we first look at the A in ACTG and the C in CTA. We have three options, so that branches off into three paths. If we add a gap to ACTG, then we are looking to compare sequences ACTG and TA. If we add a gap to CTA, then we are looking to compare CTG and CTA. And if we attempt to align a mismatch, we are looking to compare CTG and TA. Each of these branches will recursively determine the minimum cost for their corresponding input, and we will add +2, +2, and +1 respectively to these results. We then pick the minimum from those as our final answer for the original input of ACTG and CTA. However, such a recursive algorithm is naive and results in a lot of redundant calculations. If we expand a recursion tree, we can see that our nodes are recalculated multiple times. Consequently, the time complexity of the algorithm is big O of 3 to the n. A simple fix would be to remember the output for any given input. That way, if we see the same input again, we can use the output copied from before instead of reperforming calculations. To do so, we can use a hash map. The hash map will map the input to the output. If a new set of input is received, perform the calculations, and once the output has been calculated, add the pairing into the map. If a set of seen before input is received, simply return the values stored in the hash map. This is a process known as memoization. It cuts down on unnecessary calculations and significantly reduces the time it takes to compute an answer. Memoization is a form of dynamic programming and has a top-down nature as you start off with a larger problem and work on smaller subproblems to find the answer. However, we can also implement a solution using tabulation, a bottom-up form of dynamic programming. Instead of starting with a larger problem, we work on the subproblems first and then use those results to compute the answer for the bigger problems. To implement a bottom-up solution, we first build a table that represents our problem space for our input ACTG and CTA. The size of the table is dependent on the input. If the two DNA sequences have lengths of A and B, then the table should be of size A+1 and B+1. For our example, our table will be of size 5 by 4. We will see why later. This table will essentially act as our hash map, and it will store the results of the subproblems within specific cells. I find that the most important part of creating a tabulation solution is to establish what the value of each cell represents. To better visualize the purpose of this table, I will add the input as labels for this table. You will understand the empty symbol in a second. We will state that the top left corner has the answer to the smallest possible subproblem. In this case, the smallest subproblem would be an input of two empty sequences of DNA. That is why we have the empty symbol, and also the reason why the table is of size A+1 and B+1. The bottom right corner will have the answer to the input we want the answer for. In this case, that will be for ACTG and CTA. Any given cell at row I and column J will store the minimum edit distance for DNA sequences starting from J leftwards and I upwards. So, for example, the cell at row 2 and column 3 will contain the minimum edit distance for DNA sequences TA and CTG. We can see here that this table is actually very similar to the hash map. If we look at the bottom right corner, aka where our original input is, we can see that it will compute its value based on the results stored in the cell above it, to the left of it, and a top left diagonal cell. A hash map will store the results at various indexes depending on the hash function, but for our table, the results will be stored at very specific cells. Take some time to visualize this and become familiar with it, as it is the crux of this algorithm. So we can see that the value at the top is used if a gap is added to the top string, the value on the left is used if a gap is added to the left string, and the value on the diagonal is used if a mismatch or match alignment is attempted. So depending on the direction that is eventually chosen, we will add a certain cost. For top and left values, we will add +2, and for diagonal values, we will add +1 or +0, depending on if it was a mismatch or a match. If we fill the table from the top left corner down to the bottom right corner, then we will always have the values we need to calculate the value for each cell. To begin the tabulation process, we need to fill in some known values. We know that for two empty sequences, the minimum edit distance is 0. We also know that if one of the sequences is empty, the edit distance is equal to 2 times the length of the other sequence, as only gaps can be used, no mismatches or matches. So our first row and first column can be filled in like so. From there, we start off calculating the value for the first empty cell in the top left. If we take from the top cell, that is the same as adding a gap to the top string. A gap costs 2, and the cell above has a value of 2, which results in a total cost of 4. If we take from the left cell, that is the same as adding a gap to the left string. So we have another cost of 2, plus the 2 that is already there to get a total cost of 4. Finally, if we attempt a match/mismatch, we can see that G and A do not match, which will result in the cost of 1. The diagonal cell has a value of 0, so a total cost of 1. So we have options 4, 4, and 1. We want the minimum, so we choose 1. We continue this process for all of the cells. Feel free to try to fill out this table yourself. Now, we are about to fill in the last cell. If you go back in the video to 1 minute and 55 seconds, you can see that we are dealing with the same exact values. We follow the same pattern, and we have a final value of 3, which is what we expected. Interestingly enough, the path of the lines from the bottom right corner back to the top left corner represents the sequence of operations needed to get the minimum edit distance. I hope this video helped you in understanding dynamic programming more. In my experience, tabulation confuses people the most, but if you're able to draw the connection between tabulation and memoization, you might be able to understand where it comes from just a bit better. Thanks for watching.